Stanford University.
Oh, welcome to EE 380, Fall 2011-2012. I'm Andy Freeman. The other course organizer is Dennis Allison. Taxonomies and symmetries are important tools for understanding the world. When there's a hole, it's often due to either a lack of understanding or an unrealized opportunity. That's what led Maxwell to introduce flux in his equations and Dr. Lian Chua to propose memristors. It took a little longer to actually to figure out the to demonstrate memristors and then figure out how they worked. But it appears that we're now about to see commercial products just 4 years after that, which makes it one of the fastest fastest transitions from lab curiosity to actual commercial product. Today's speaker, Stan Williams of HP, has been instrumental in both the understanding of memristors and their imminent commercialization.
Thank you very much. I appreciate the opportunity to come here, and I appreciate that there's still some people like me who believe in live events. It's great to actually have real people to talk to. So what I want to do is just give an overview of what we've been doing in this with this curious thing called the memristor. It has only been 3.5 years since we published our first paper in the area, but since then we've written over 50 more and submitted them, and about 35 of them have been published. And so in fact, I have about a dozen lectures that I've prepared in this area that I have been giving in various places around the world, but for some reason not across the street here at Stanford yet. But what I've done here is I've essentially taken some of the highlights out of those dozen lectures, and perhaps if there's other opportunities I could come back and dive into more detail. This presentation here is really just going to be sort of clipping off the tops of the trees and looking at some of the higher level issues. First of all, what I need to do is really acknowledge the fact that there have been a huge number of people who have been working on this with me for it's over 13 years now. I actually made the transition from academe to Hewlett-Packard Labs in 1995. I was actually hired by David Packard and started thinking about what would be important for the future of the HP company. I mean, I was hired with the idea of starting up a basic research group, but I was given the charge of coming up with some sort of a technology that was going to be important on something like a 10-year time frame. So that was both a huge responsibility and opportunity, and I'll tell you a little bit about what I started doing and how we sort of wound up where we are. But there have been over 60 current and former members of the laboratory that I have now at HP who have worked with me on this, and over 40 members of other Hewlett-Packard organizations, as well as probably something like 200 graduate students and professors and postdocs at universities at many institutions. So it's really impossible to put them all here. And just to say that this is really the attempting to summarize the hundreds of researcher years of effort in this area. So this is not something that just sort of, we stumbled across it by accident. The research group that I'm privileged to lead now within HP has a lot going on. We are still doing very fundamental material science and physics, looking further and understanding more about what's going on. And we use a lot of that very fundamental work to inform our ideas about specific devices and really create SPICE models for those devices, and so that we can put those in the hands of circuit designers. We have circuit designers who are designing new types or new ways of doing old things for the most part. Then we essentially do modeling of those circuits, and we also build exemplars of them, test them, and of course they don't work. But then what we do is we give that to our error correction code guys, our information theorists, and they figure out really cool ways of introducing just a small amount of redundancy in the circuits to cover up all of the nasty errors that there are, and then we essentially iterate and improve. And that's sort of the way we work. I'm really only going to be talking about this little part up here, what we're essentially the device part itself, for the most part. We do have a commercial effort. We are in the process of trying to introduce a memory product, which would be a competitor for flash memory. I get in trouble when I say when I think this is going to appear, so I'll skip that this time. Keep my head on my shoulders, but suffice it to say, I don't think it's going to be in the deep dark future. This is not something that it's still 10 years out. It's much closer than that, and we are building. We're in a couple of different fabs. We're making 300 millimeter wafers. We're making very good progress on the commercialization effort, and of course I still have this. I actually was up in Redmond a while back, and I was giving a talk there. And what I did was I slipped a view graph into my stack, which was the blue screen, and I had it show up, and I said, "Oh, does anyone here know anything about Microsoft Vista?" And they all looked at me and they said, "No one here uses that." Oh well. Okay. So when Dennis invited me to give this talk, he teased me a little bit, as he should have. He said, "Well, the last time you gave a talk before this audience was in October 9th of 2002. And so I went back and I looked at the slides that I presented then, and they were sort of embarrassing. I will say, but this is one of the view graphs that I presented then. And what I was talking about was the need to come up with a new type of switch, a switch that would allow us to sort of turn something on and off very reliably and quickly. And what I was speculating was that the physical mechanism behind that switch would be a tunneling barrier, whereby I could either modulate the width or the height of the tunneling barrier in order to achieve a very large change in current flowing through this switch with a very small change in a physical parameter of the device. And so that's what I actually started looking for in 1997. I thought I had found it in 2002, and I came here and I gave a talk about it. And what was it? Well, it was a molecule. We were working with some chemists, some colleagues of mine at UCLA, and we had this funny little molecule, and we would put this in a junction, and we got this current voltage characteristic, which we called a bow tie, and it had a lot of these characteristics that we wanted to have. We had this, we thought we knew what it was, how it was working, but you can see that it was operating in a very low voltage range. It was switching, it was changing its resistance by orders of magnitude, and the only problem is it didn't last very long. It would burn up. And so we were sort of stuck for a while trying to figure out what to do. So that's what I talked about 10 years ago. Dennis also teased me a little bit because he said, "All right, you also made a very brash prediction in that talk in 2002. You said that by now, by 2010, that CMOS would have essentially hit its limits." And what I'm going to claim is that I was right. Okay? Because if you look at this chart here from the National Academy of Science report from 2010, you can see that in fact, roughly in the year 2005, there has been a sharp right turn in an awful lot of properties of CMOS chips. So in fact, what's happened is that the performance per core in CMOS has topped out. It's hit its limit. And what we're doing now is we're making more transistors on a chip, but we're not actually getting more performance out of any individual component on that chip. We're making more components, we're making more cores. And then it's up to the poor programmers to figure out how to actually utilize those cores and get some sort of higher performance out of that. So I will essentially, say that I wasn't too far wrong, that I was sort of right. In my previous talk here when I said that CMOS was going to hit its limits, and that it needed something else. There was something else that we need along with CMOS to sort of get over some roadblocks. And what are those roadblocks? They're essentially obviously not having to do with computation anymore. Computation is not the roadblock. It's not the limiting factor in our computing systems. The roadblocks are essentially moving data, getting the data from where it's residing to where you want to do something to it, and also just the cost of storing and keeping the data where you've got it. And so there's really two issues that we feel, at least in my lab, that are really going to essentially cause a rebirth of Moore's law, if you will, a rebirth of the increase in performance per unit, and that's going to be dramatically improving the ability to store data and to move it. And so I'm going to talk about the store issue for the rest of this talk. So let me give you a very, very brief history of the memristor. For, well, something like 150 years or so in electrical engineering, we had three fundamental passive linear circuit elements. And in fact, if you're working in a world which is completely linear, there can only be three. There's an issue of dimensionality here. 3 dimensions, 3 linear circuit elements. And those are the resistor, the capacitor, and the inductor. And you can see that the last of those was essentially discovered simultaneously by Michael Faraday and Joseph Henry in 1831. And that's actually not a cigar. That is an inductor. And we have had these tools to work with. We've had this basis set to work with for a very long time. Now, people say, well, what about the transistor? Well, a transistor is, of course, it's an active element, and it really has an equivalent circuit which involves resistors and either current or voltage sources, depending upon whether you have a Norton or Thevenin equivalent circuit. So the transistor, of course, is a different type of entity, but it doesn't sort of belong within this fundamental basis set of passive devices. Now, in the 1960s, there was this curious character named Leon Chua, who essentially did for circuit theory what Einstein did for Newton's laws. What he did was he took the elements of circuit theory and he generalized it to nonlinear systems. All right? And so in doing so, he went from 3 to 4 dimensions effectively in what he was looking at, and he essentially saw that there was a hole, when you're thinking about nonlinear systems, in the basis set of passive circuit elements that should be available. And this hole, he did more than just sort of note it. What he did was he said, well, there actually should be something there. Something should fill that hole. And he took the mathematics that was available to him, and he constructed a mathematical model of what that thing should be. And what he found out is that it was a resistor with memory. So he called it memristor, which is awfully difficult to pronounce, by the way. But it's a portmanteau of memory resistor. And what it is, what you find out by looking at this, without going into much detail, it's a non-volatile resistive memory. So this really was a mathematical prediction. And what he did was, in his paper, in this 1971 paper, he proved mathematically that there is no equivalent circuit to M that could be made using any combination of R, C, and L, any nonlinear set of devices. And because you could not duplicate what the memristor could do using these, he essentially said, well, then this must be as fundamental as these other three. So that was the viewpoint that he had. And he published the paper in 1971, but the title of his paper was Memristor, the Missing Circuit Element, because he didn't know of a physical example of this thing. It turned out neither did anybody else at the time. He then generalized the concept in 1976 along with his graduate student, Steve Kang, who was recently the chancellor of the University of California at Merced and has now gone back to UC Santa Cruz. But they essentially wrote a paper in which the title of the paper was Memristive Devices and Systems. And so what they did was they took the very simple ideas and simple model that Leon originally proposed in his 1971 paper and generalized it even further. And what they found is that the memristor actually requires 2 equations to describe thoroughly. In fact, there is for the memristor what is essentially at least one or more hidden variables. That hidden variable they called a state variable, and what it does is it represents a physical property of the device. There's something inside the memristor that changes, and it's that thing, that state variable, that provides the memory for the device. So you actually, if in this format here, it's best to write out the memristor equations not as something involving flux and charge, which gets people all confused and crazy, but to write it in terms of voltage and current, but to do it in two equations, in which one equation is called the quasi-static conduction equation. And here, this looks just like the standard, resistance or voltage is equal resistance times current. But the difference is that the resistance is a function. It's a function of this state variable. And the state variable itself is a function of the current, for instance, that flows through the device. All right? And so you've got two equations, a dynamical system here that describes what this device is going to do. And so you need to understand what this state variable is. And I think that this was really the thing that just confused people like crazy for a long time. I know that, frankly, I read these papers for 3 years and really couldn't understand them at all. It took me a long, long time before I finally figured out what was going on. And in part, it's because the papers are written as a series of theorems and proofs of the theorems. So this is not the general way that a lot of people think about. And it was kind of a strange, Leon is really a mathematician more than anything else. So it was just a strange way of trying to figure it out. But if you sort of keep at it long enough, you eventually do get through. It took me 3 years. I'm sure that a lot of other people could get it much faster than that. But at the end of the day, what do you wind up with? What makes the memristor fundamental? Well, rather than look at Leon's mathematical proofs, you can sort of look at the current voltage characteristics for nonlinear devices, and you see the resistor, the capacitor, and the inductor. Capacitor and the inductor sort of look the same, except what you realize is that they're 180 degrees out of phase with each other. And then you've got the memristor here, and it should be just sort of obvious by inspection that there's no way of connecting these three things up, or any set of these three things up, into a circuit that will give you that. Okay, so that's really, in a sense, why it is fundamental. And why is it useful? Well, it turns out, whoops, sorry about that. It turns out that this characteristic IV curve here is very difficult to fabricate. You can build an equivalent circuit using transistors to make this IV curve, but it takes about 15. And a few capacitors and then some other things as well. So in fact, or at least in theory, if you did have a memristor and you looked at a set of different types of integrated circuits, you could reach in and pull out a dozen transistors and reach in and replace those dozen transistors with a single memristor. And if you could figure out how to do that in sort of a large-scale basis, you would have a new way of achieving Moore's law, if you will, not by making transistors any smaller, but by effectively replacing transistors with a passive device that allows you to achieve the same thing as a significant number of transistors. So this is a way of effectively not attempting to replace CMOS by any stretch of the imagination or replace transistors, but give it essentially a power boost, a supercharge, by inserting this functionality, which is very useful. So in my lab, we had been working on this molecule, this molecular switch thing that we were playing with. But as I started looking in the literature, what I realized that people had been seeing interesting current voltage characteristics, what we called bow ties, and what Leon called pinched hysteresis loops, for a long time. We essentially went all the way back to the 1960s. In fact, there's a review paper in 1970, the year before Leon published his paper, and in this review paper there was over 150 references to people in the 1960s who had essentially done experiments in which they had put probes on things, and I mean all sorts of stuff, ceramics, polymers, anything that you can think of, and seen hysteresis loops, or these pinched hysteresis loops, things that look like this. So there is a huge history of people who have done that, and it stretches up until the present time. There's at least 1,000 papers now that have been published in which there were pinched hysteresis loops. But what I would say is that it's highly unlikely that any of these people ever read Leon's paper, and frankly, it was also certain that Leon never read any of their papers. I mean, if he had, he might have just glommed onto this right away and said, oh, that's got to be a memristor, but he didn't. So that's sort of where I came into the story. I just got lucky. So we were playing around, and what I realized, we started playing with a system, and what I realized was that we had these interesting molecular devices, but I could take the molecules out and the device still worked. Okay? That was intriguing. And so here is a picture of devices that we were making. These were actually this is a picture of a quite large one, but we were making devices anywhere from 16 microns across using shadow mask all the way down to 30 nanometers. And no matter what the size of the device, we would get these current voltage curves that look like this. Very characteristic shape. And I saw that, and I said, that just looks so much like like this pinched hysteresis loop in Leon Chua's paper. Could it be a memristor? I mean, and if it is, why? I mean, what is it about this thing that gives it this characteristic shape? And sort of the other question I had was, does anything with a pinched hysteresis loop, is that a memristor? Well, it turns out that I now know that it is true that anything with a pinched hysteresis loop is a memristor. Boy, say that fast. And actually, Steve Kang and Leon proved it mathematically, but I couldn't understand the proof. In fact, I couldn't even understand what the proof said. But Leon has written a very nice tutorial paper now. It was published earlier this year in the journal Applied Physics A. It's a European journal, Springer journal, and it's like a nice 30-page long tutorial in which he goes through it. Instead of trying to prove a whole bunch of proofs, he just sort of really sort of takes you by the hand and leads you right up the primrose path and shows you what's going on. So if you're curious, I recommend that significantly. However, Leon is not a physicist. He's not he's a mathematician who works in circuit theory. And so he didn't understand what physical processes could yield this interesting pinched hysteresis loop property. And so what I did in thinking about titanium dioxide, I did a lot of reading in many different areas of science. Geology, it turns out, ceramics, physics, EE. And from all of that, I finally was able to piece together a very, very simple model, so what I call the freshman level model. And this is the basis of the paper that we published in Nature in May of 2008. And the idea behind the model is that titanium dioxide is a very interesting material. In its stoichiometric state, TiO2 is a wide bandgap semiconductor. It has a 3.3 eV bandgap. And if you therefore have even a fairly thin, few nanometer thickness layer of TiO2 between two electrodes, you've got a very good resistor there, and electrons can only tunnel through it. So you've got a very high resistance. However, if you remove some oxygen from the lattice and think about auto-doping the material, you can auto-dope titanium dioxide just by pulling oxygen ions out of the lattice, and what's left behind are oxygen vacancies. Those oxygen vacancies are dopants in the material, and in fact you can pull out as much as a few percent of oxygen ions from the lattice, and so you can dope this material essentially to metallic levels. And so you have a very interesting metal insulator transition here. And so if you have a piece of material in which there is stoichiometric material here, which is insulating, and you've doped some thickness of the material here with oxygen vacancies, and you then apply a voltage, you can actually push the oxygen vacancies to the left. They will drift in the field, and they will cause the width of this tunneling barrier to get smaller. So this is exactly the model that I originally came up with for the device I wanted to make in 1997. So I was sort of prepared for it in some sense. I wanted to make a tunable tunneling gap, and I thought, wow, I mean, that's exactly what will happen in titanium dioxide. So this is the simple model that I came up with, and what I did was I realized that what I've just said in words, I can write down a static conduction equation here. The voltage and the current are related by a resistance, and the resistance is a function of a state variable W, which is the width of a tunnel barrier. And W, the width of the tunnel barrier, is essentially, if I take the derivative of that, that is the drift velocity of the oxygen vacancies in the field. And so these two equations here are exactly the memristor equation. And so I was able to write down a very simple equation for the memristance for this freshman level model. And one interesting thing that you see is that the size of the memristance is inversely proportional to the length or the width of this area here, the width of the active region. And so what that says is that memristance gets stronger the smaller your device. You make the device smaller and smaller, the memristance gets larger and larger. And so this is one of the reasons why it was so difficult to really understand and see memristance reliably in the 60s and the 70s and the 80s, and even in the 90s. We weren't making nanoscale devices. But in the last decade, we've been making nanoscale devices, and all of a sudden memristance started jumping out all over the place. Yes, question?
So were you trying a titanium dioxide semiconductor, or were you just trying to use it as an insulator and found out that by accident it had these semiconducting properties?
At the time, I didn't know what the hell titanium dioxide was. I was just trying to make a switch. And I didn't care whether it was insulating or semiconducting or whatever else. And everything that I'm telling you now is what I've learned since then. Okay? So the issue is that memristance actually is a universal property. It's a universal electric circuit property. It's everywhere. But if you have a big device, it tends to be very small. If you have small devices, it tends to get big, and it tends to jump out at you. And so if you look at literature right now on all sorts of devices, nanoscale transistors, this, that, whatever else, you see hysteresis loops. And if you read the papers, people will say, oh, well, this is some sort of anomalous capacitance or this or that or whatever. No, it's memristance. It's not a capacitance. You can tell it's not a capacitance because these hysteresis loops are pinched. They go through zero. If it was a capacitance, it wouldn't go through zero. So in fact, people have been seeing memristance all over the place for a very long time, but they just didn't realize it. And so we published this paper. We called it "The Missing Memristor Found," and it was tongue-in-cheek. You know, we didn't claim that we had discovered these things. We said they've been around lying on the street for the last 50 years, and nobody had ever picked them up. All right? Now, that was the freshman level model. At the level of, say, a senior, you've got to get a lot more sophisticated. And so at that level, what you realize is that not only do you have drift, there's also diffusion and other issues going on. And so if you want to make a model of how these devices are actually working, you need to ask how are the electrons and holes and the dopants, these ions and or vacancies, moving, and how they affect each other in the presence of the Poisson equation when you put a bias voltage across this. So in fact, in this particular model here, memristance emerges as the coupled motion of atoms and carriers in the device. Right? You put a high enough electric field across the device, and if it's big, and if you have something that's only a few nanometers in thickness, a volt is a huge electric field. And so that field is actually enough to move atoms, and if you can move those atoms in a reasonable way, which is reversible, you can make an interesting electronic device. And so it's actually a solid state ionic and electronic device where the ionic and the electronic degrees of freedom are coupled. And that coupling comes from those two equations, that static conduction equation and the dynamical equation. So that's the viewpoint. My postdoc at the time, Dmitry Strukov, and I essentially worked through the equations. We did a bunch of simulations. And then what we started to realize was that there's actually something else that can rear its ugly head in all of this. And that is not only is there diffusion, and which is essentially movement of particles in a concentration gradient, and drift, which is the movement of particles in a electric field, but there's also thermophoresis. These devices are just guaranteed to have huge temperature gradients inside them. You've got very, very small dimensions, you're running currents through them, and so you can tell that because of the heat sinks in these things, that there's going to be very large thermal gradients both axially and radially in these devices. And so and those can cause things to move too, and so you need to actually consider all three of these things simultaneously. What we actually tried to do that. We tried to write a program that would do all of that. We sort of put it up on a big chunk of a machine that we've got at HP Labs, and nothing ever came out of it. And what we looked at what we found is that there's just too many equations, they're too nonlinear, they're too stiff, and you just simply can't solve them all in 3 dimensions in any finite amount of time to get something out of it. So what we did is we started simplifying and we started looking at limits. So one limit is just looking at the drift diffusion model, and this essentially explains this bipolar switching phenomenon. And here what you see are a set of very simple one-dimensional simulations or calculations that we did using the drift diffusion equations. In this particular case, we start off here with the device, call this in the on state, and so we essentially assume that there was a constant concentration of oxygen vacancies throughout the device. We put a positive bias on this side of the device here, and what that does is it pushes the oxygen vacancies to the left like this, and when you do that you open up a tunnel barrier here, and that turns the device off. Now what you notice when that happens is that you're essentially piling up, you're getting a higher concentration of vacancies here. So what you've got is the drift going in this direction and the diffusion going in the opposite direction, so they're opposed to each other. However, when you turn the device back on, you actually have the drift and the diffusion are both pointing in the same direction. The high concentration here is low concentration there, so diffusion wants to go in that direction, drift wants to go in that direction, and so that creates essentially an asymmetry in the on and off switching of the devices. And actually I'll just sort of skip back here quickly for a second, sorry about that. And that's this asymmetry that you see right here. Right? For off, the off is slow, the drift and diffusion are opposite to each other. On is fast, drift and diffusion are operating in concert with each other. Okay, another limit that we looked at is the limit of thermophoresis. For thermophoresis, it turns out that vacancies want to essentially move up a temperature gradient. If you sort of think about it, if it gets hot, that's where you want the density to get low. So vacancies move up a temperature gradient and away, and they will diffuse away. So you have drift and diffusion sort of opposing each other, and you have thermophoresis and diffusion also opposing each other. But for the drift, the thermophoresis case, we considered a radial switching. In this particular case, we looked at essentially vacancies essentially moving in and moving out. And there, what you find out is that it doesn't depend upon the potential, the sign of the electric field. You can get switching. And so those of you who are familiar with switching in these materials, you know that there's actually 2 kinds. There's something called bipolar switching and unipolar switching. So the unipolar switching comes from this thermophoretic effect, where you've got things that are moving radially in and out, essentially following the temperature gradients. The bipolar switching is an axial motion in which things are following the electric field, but of course in any real system you've got both things going on simultaneously. And so any real system is very complicated because it has both axial and radial forces acting on them, which are resulting from thermal gradients, electrical gradients, everything else. And so these are very, very complex devices. Attempting to write a differential equation solver to do the completely general 3-dimensional system has turned out to be completely beyond us anyway. So we've been playing around with approximations. We've been looking at analytical solutions to the diffusion equation for instance, like this. This is a very famous one. Turns out to be very interesting, and we can understand a tremendous amount about at least the qualitative behavior, and we can parameterize the behavior of the devices. For instance, these devices, the bipolar devices, actually have a switching time which has a log normal distribution. And it turns out that we can exactly understand that in terms of a simple drift diffusion equation here, like this. So we're still struggling with the theory, and one of the things that we're just now starting to do is actually molecular dynamics. And here what we do is we put a bunch of vacancies. We put a bunch of vacancies into a system. So the red are vacancies, and then the background is essentially titanium dioxide. And we put a positive bias voltage here, pulse it, and then we just watch what happens to the vacancies. And here, of course, what you see is that things aren't uniform as the differential equations want them to be. They're discrete, and so you actually have both attractive and repulsive forces between the vacancies themselves, and so they wind up forming these strings and these voids and filaments, if you will. The average behavior of this follows a differential equation, but of course in any particular event that you've got this stochastic behavior, and so any real device will show essentially stochastic issues associated with them. So no two switching events are the same. It's not some continuous system evolving, it's the fact you've got these discrete vacancies which are moving, and that provides some entertainment, shall we say, as you try to think about how to use these as real devices in a system. All right, so how do you actually take a memristor and test it and understand what its properties are? Well, what I'll tell you is that the thing that you don't do is you don't put it on a curve tracer. I mean, the only thing that a curve tracer will tell you is if it is a memristor or not, because you'll see if you've got a pinched hysteresis loop. But other than that, curve tracers are completely useless for trying to understand anything quantitative about the device. And the reason is that curve tracers don't understand dynamical devices. Curve tracers don't have a timestamp. What they do is they will do auto scaling, and they will try to get the best possible signal to noise ratio. But what's happening is all of the curve tracer is trying to set, okay, I want to measure this point here, puts a voltage, and because it's a memristor, the current is changing. And so the curve tracer is going nuts trying to figure out what to do. And actually, we've gotten to the point to where we can look at somebody's data in the literature, because I guarantee you that everybody else is using curve tracers to look at their memristors. We can look at a paper, we can look at their data, and we can tell you the model of the curve tracer that they're using, because each one has a little bit different firmware, and they each go into slightly different types of oscillations when they're testing a device. And so they will look at this behavior and they say, oh, this is crap, this device is terrible, look at this, look at all this funky stuff going on here. Well, okay, that's actually your curve tracer and the firmware on your curve tracer not understanding how to actually collect the data on the device. So how do you collect the data for the device? Well, you actually have to do it in a two-dimensional fashion. Remember, there's two equations you have to figure out: the static equation, quasi-static equation, and the dynamical equation. And so the device has state. And so what we do is what we call a state test. And it takes a lot of time and effort to do this. The way we start off is we first measure the state. And so we measure in a 4-point probe apparatus, we measure a voltage sweep and the current sweep, both independently as a function of time. So here is time, if you will. So we measure current and voltage, and that tells us the state of the device at this point. Then we pulse the device. We apply a voltage pulse to the device, and what that does is that causes the state of the device to change. Then we pull it again, or we probe it again, measure the state of the device, push it, measure, push, and what you see is that the width of the pulses gets wider, actually exponentially wider, each time we pulse the device to evolve the state. And the reason we do that is we want to look at the properties of the state over many orders of magnitude in time. So we start, if you start off with a very narrow pulse and you want to look out 7 or 8 orders of magnitude in time, it can take years to do such a measurement. Well, we're impatient. And so we essentially, in this particular set of experiments, we went from 1 microsecond to 33 seconds in 440 pulses. So you actually collect 440 different IV curves for each pulse, and then you reset the device back to the initial state, and then you got to do the whole thing all over again at a new voltage, and then reset it, and then do it again at a new voltage. So after you're done, you have several thousand IV curves, and what you want to do is from those several thousand IV curves, you want to get a state variable out. So for this particular device, which is a titanium dioxide device, what we found is that these IV curves, every single one of these several thousands of curves could be fit to the Simmons tunneling equation with only one variable changing, and that was the width of the equation, the width of the variable, the width of the tunnel barrier. Okay? So what we're saying is that in this particular case, as we were sort of postulating, the state variable of this device is the tunnel barrier width. We've got one equation that we can use to fit several thousand IV curves, and there's only one variable that comes out of it, and that's the tunnel barrier width. So we can then take the tunnel barrier width, and for both off switching of the device and on switching of the device, we can plot the tunnel barrier as a function of time, like this. And what you see in these devices is that this device is changing its resistance by 3 orders of magnitude by the tunnel barrier width changing from about 1.2 nanometers to something like 1.7 nanometers. So we're actually changing the effective tunnel barrier width in the device by half a nanometer. This is truly a small change in the system, and the same for on switching like this. And so what we've done is using both some seat of the pants theory, trying to approximate the behavior of these with analytical equations, and then doing some fitting, we've come up with expressions for the time dependence, essentially for the drift and diffusion velocity of the edge of the tunnel barrier. So that's what this is. And it's pretty funky if you look at it. It's got a hyperbolic sign, it's got an exponential of an exponential, it's got all sorts of stuff in it. It's highly nonlinear, extremely nonlinear. And boy, is that great. I mean, if you're trying to figure out, if you're trying to do computation, if you want to do multi-level storage of bits in something, you want to use this for some type of logic device, the more nonlinear that you can make it, the better off you are. And this thing is extremely nonlinear. So this is actually very, very exciting for doing computation. But the main reason that we do this is so that we can create a SPICE model. So we take these equations here, these equations right here, and we put them into SPICE, and that allows us then to actually look at now a current voltage plot. I mean, before, we got the equations by doing this state variable test, but we can now, using SPICE, we can actually reproduce, in a very good fidelity actually, the IV curve with a fairly small number of parameters. I mean, the number of parameters that are used for this is actually very small compared to what people use for transistors nowadays. So we have very good SPICE models that we can use and put into the hands of our circuit designers for them to be able to go off and design circuits using these devices that we've tested. So that's, and then of course we'll go off into the fab and foundry and play all sorts of games. So we're not going to follow that thread. But coming up with this structure, this electronic model gives us a structural model as well. And so we wound up doing a huge amount of physical characterization. So we did a lot of work at multiple different synchrotron radiation sources. We've done a lot of work here at Stanford. Using TEMs around the world. We've had a guy who's essentially just been the world trekker, going to every facility that we can think of that can give us some piece of information on looking at these things. But this model that we had of the device essentially says that there has to be some sort of a conducting channel in the device. Remember I told you that there's this radial type of motion and axial type of motion. So our model tells us that there has to be some type of a channel, what we call a conducting channel in the device. And so you form that channel in most cases just by operating the device a few times. And so here was a very simple experiment that we did. We just peeled off the top electrical contact and looked at it with an AFM, and sure enough, every time we do that, we essentially pull off this little area here, and we can see this thing right there in the device, and that's our channel. That's our conducting channel. It actually was tricky to identify what it was. In order to do that, we actually built some devices on some very, very thin silicon nitride membranes, and actually did both X-ray transmission and scanning electron microscopy on an active device. So we were able to actually switch the device, do X-ray spectroscopy on it, switch it some more, put it in a TEM, do transmission electron microscopy on it, all the time sort of going back and forth on the same device. And so, without getting into a lot of detail, what we were able to find is that for a particular type of device, this is a very large one, which went through a process called electroforming. In other words, we had to put a very large current through this thing in order to sort of make it work the first time. What we found is that there was a very special site, this conducting core, conducting channel in the device, and we're actually able to look at it and see that it was reduced titanium dioxide, and we were even able to exactly determine each of the different phases. And what we found out is that this thing is Ti407. Ti407 is a substoichiometric, it's called a Magnelli phase, and it's metallic. Okay? But you can also think of it as a phase of condensed oxygen vacancies in TiO2. And so in fact what happens is you get a little core, a channel of Ti407, and that is a source and sink of oxygen vacancies. And you put a bias voltage on that, you can extract oxygen vacancies out of it and essentially cause them to drift into a thin film of TiO2. Reverse the bias voltage and you can push the oxygen vacancies back into the Ti407. So that was a theory. So we actually built devices based upon that theory. And so that eliminated this process of electroforming, which is kind of inconvenient, shall we say. So now when we build devices, we actually intentionally put in a layer of a source and sink of oxygen vacancies, in this case Ti407, and then a very thin layer of TiO2 on top of that. And now what happens is this layer essentially is where the oxygen vacancies reside. If I put a negative bias up here, that pulls the vacancies into the TiO2, that turns the device on. If I put a positive bias here, that pushes them back out, turns them off, and we can get switching curves that look like this, that do not require any of this electroforming stuff. So that's actually very nice for devices. Now, let's talk about speed, energy, and endurance. People always want to know about that. So at the end of every talk, people would always ask me these questions, and I always used to have to go, oh gosh, I don't know. Well, now I do know, and so I can answer the questions. And so people always want to know what are the switching voltages that are required? Oops. What are the speeds and energies for switching? What are the on to off ratios? What's the retention time? What's the endurance? What's the scaling limits? All of this stuff. So we've actually gone through all of this, and we figured all of this out. When people used to ask me, how fast will these devices switch? My answer used to be, well, I don't know, because we've never been able to measure them, because all of our measurements are limited either by our measurement equipment or the straight capacitance and series resistance in our system. Well, we finally fixed that by building a microwave strip line system. So we now have a microwave tester in our group, a probe station with very, very fast oscilloscope. We've built a microwave strip line system, looks like this. And so we have a probe here, coplanar probe, strip lines, and we actually build our memristors right in here, right in the middle of this strip line. And so we can actually send a pulse, a very fast pulse down this thing. Part of the pulse transmits through, and we can detect that, and part of it reflects off. And so this effectively allows us to do a 4-point probe measurement in real time with a time resolution of a picosecond, roughly. The answer is, we're still limited by our pulse generator. We send 100 picosecond pulses down the strip line, and these things switch in 100 picoseconds if the pulses have a pulse height of 2 volts. So that's actually kind of cool if you think about it. That says that they're moving at least 20 meters a second. that the vacancies in the device, when you're hitting them, they're moving 20 meters a second. Seems real fast, but actually it's not that fast compared to the speed of sound in the materials. And so it's, it's not crazy, but what it's telling us is that that we can at least switch these devices. We can get these oxygen vacancies to move a half a nanometer in 100 picoseconds or less. And now I got to go buy a new pulse generator so we can actually see what the true speed is. But we're well below a nanosecond, which is great. At the same time, what we can do is we can look at the transmitted and the reflected waves, voltage pulses, and that allows us to understand both the applied voltage and the current through the device. It's just like doing a 4-point probe measurement. And we can do that with a time resolution of about a few picoseconds, and we can turn that into an energy plot as well, because we know both voltage and current as a function of time. And here's something very interesting that we see. These devices, essentially, they switch in this particular case, we're biasing them to about a half a volt. They switch in a nanosecond or so, but it only takes it takes less than 2 picojoules to switch the device. And what's interesting is that the switching is over after you've applied 2 picojoules. If you apply any more than 2 picojoules, the device doesn't change. And so in fact, the way you actually really want to hit these devices, you want to hit them with a very short pulse of a couple of picojoules. That switches them. All of the switching occurs within just a couple of nanoseconds and within a couple of picojoules of hitting the device. And so that's actually kind of nice. What that tells us is that these devices will not be limiting in any circuit into which we insert them. We don't have to worry about these things sort of slowing down your CMOS circuit. These are going to run absolutely as fast as the CMOS in which they are embedded. And so really what still slows the CMOS down is not these things, but the RC of the circuit itself. So that's just a good piece of news, but we're still going to pursue this even further and understand really what the limits are and how far we can go. But at least as of this point in time, people want to know how fast do they switch. Well, certainly, 100 picoseconds or less, how much energy? Well, for on switching, because that's the easy part, less than 2 picojoules. For off switching, it's harder to do that. So that's maybe 10 picojoules. Turn them on and off well over 1 billion times. Here's 1 billion cycles here. We did this device a year ago. And by the way, this device has not died. It's still alive. We're still testing it. It takes us 3 months to accumulate 10 billion cycles. And we don't only have so much equipment, so we actually test the device for a while. We put it on the shelf, bring it back. And so when we can put this device on the shelf for 3 months at a time, we look at it, it doesn't change. Then we test it some more, and then we're going back and forth. So we're sort of looking at endurance, but if you look at what we're trying to compete against right now, we're trying to compete against flash. Right now, SLC flash, do you actually know what the spec is for SLC flash? Okay, yeah, okay. It's down here. That's the spec for SLC flash. Here's where we are now. Actually, it turns out that some folks at Samsung saw our paper, and so they took a device very similar to ours and just put it on a pulsar and just ran it for a bunch of time, and then looked at it and said, oh, well, we got 10 to the 12 pulses, but they didn't look at any of them. So they don't have any idea what, they know that they could pulse it 10 to the 12 times and it was still alive after that, but they've got no idea what the bit error rate was. So we haven't gotten out this far yet because we're actually trying to accumulate all of the data and get what the bit error rate is. We think that we're going to be up here someplace. We think we're going to be at a DRAM consumer replacement level, in another year or so. That's where we think that we can be with this. And the fact is that there's no reason why these things can't go even much longer than that. We just have to build a really fast tester, and we can test these things much faster than we've been doing. All right, I'm getting down toward the end. I'm going to just touch on a couple of fun things. Logic. People ask me, can you do logic with these things? The answer is yes. Fascinatingly enough, what you've been taught, what most people have been taught about doing logic has not been right. What you've been taught is that it's impossible to do logic with two terminal devices, right? Because you can't do complete logic because you can't do a NOT. You can't do inversion. Impossible to do inversion with a two-terminal device. Guess what? That's not right. Okay? And in fact, it was known in 1910 that that wasn't right. Bertrand Russell, essentially a logician, studied logic very early in the 1900s, and he wrote Principia Mathematica in 1910. And he essentially had his favorite Boolean logic function, which he called material implication. It turns out that material implication and the operation false together form a complete basis. And so you don't need NOT. You don't need a NOT. You don't need inversion to do logic. And we essentially prove that in a paper we published in Nature last year, essentially showing that that memristors naturally perform this material implication operation. And so I'm not going to go into a great deal of detail. It takes a long time to sort of describe it. But this is the truth table for material implication. And the way you read this is that Q is replaced by P implies Q. Has a very simple truth table associated with it. But essentially, this is two memristors here connected together like this with drivers. And you can essentially perform this material implication. And I can at that point and say, okay, that proves that we can do universal logic. And you say, I don't believe that. Well, okay, if we do two of them in sequence, we can essentially do an AND. Okay, so here is a NAND performed with three memristors, essentially using this two steps of this material implication. So this shows that it shows actually several things. One thing is some of the core tenets in textbooks may not be right. Okay? This whole thing about you can't do logic, can't do Boolean logic without the NOT operation, can't do it without a three-terminal device, at least at this level, is not correct. Now, to be honest, you've got to have drivers. You have to have active devices, which of course are supplying energy to the system. You have to have drivers for this. But if you think about it, these things here are very, very tiny compared to a CMOS NAND gate made from the same technology. And also, what you don't need is you don't need latches, because these things are latches. So you can perform something called stateful logic with this. Memristors are state machines. The state is encoded with impedance, not voltage, which makes it sort of interesting. So it's very low energy. There's no static power dissipation. It's a latch. It's non-volatile. And so I guess the question that I come up with here is we kind of somehow need to ask how the nanoscale world wants to compute and not necessarily impose our preconceptions on some new device that comes out. Instead of trying to figure out how to make that do an inversion, it turned out that we didn't need that. All right, so I got a couple of minutes left. I'm just going to say a couple of quick things. Oh, I do?
Yeah.
Okay. All right, so actually, in his second paper, Leon Chua said, I do know of an example of a memristor. There is an example that I can think of in the real world, and that's a synapse in a brain. Okay? So what about using memristors as synapses in electronic circuits and trying to do non-Boolean computation in a way that's more similar to the way people do their computational work? So this is a project that we've got going on, and actually many other people have sort of latched onto this as well. There's a whole community of people working on this type of idea now. The idea is sort of schematically illustrated like this. You think about building a cortical system in which you have CMOS, a lower level of CMOS here, which essentially are the neuronal bodies in a system. You then have wires, nanowires, that essentially come up from the neurons and run across and are able to make connections with a lot of other neuronal bodies. And the way they do that is through memristors. And so this type of picture here is actually intended to be to scale. We've essentially designed CMOS neurons which requires something like on the order of 10 transistors or so. So we get I'm sorry, it's 100 transistors. So it's 100 transistors for this neuronal body. And if you ask yourself, what is the ratio of the area of this neuronal body to the area of a single memristor in this circuit, it's about 10,000 to 1. So in other words, what we can do is we can actually run wires long enough to make connections to 10,000 other neurons in this type of system. And that's kind of like the number that people think about in brains. That's the number that gets thrown around. So at least the thought is that we ought to be able to perform some interesting types of computation with a system in which we are doing effectively analog computation using essentially weighted operations on the memristors in order to be able to do that. I mean, this is the subject of multiple lectures. I don't have time to go into this, but just as a very simple idea of why this is sort of possible or interesting, just think of a very simple circuit like this where we have a bunch of essentially voltage sources which represent voltage outputs from a whole set of these neuronal bodies. And then we have those voltages essentially being connected to some current output through a set of memristors, and you've set the state of the memristors. So in one clock pulse with this system, you're essentially performing a dot product. The output current of this circuit here is just the dot of this voltage, this set of voltages here, with the resistances represented by this set of memristors here. In a circuit that would trivially have something like 10 to the 9 memristors, which is very easy to do, and a clock speed of 1 megahertz, you might have the equivalent computation rate of something like 10 to the 15 flops. Now, all of that said, this is not a fair comparison, of course, because these are not 32-bit or 64-bit operations, and they will have, they'll probably only have 3 or 4 significant figures, because really it's an analog thing that you're computing here. But at least, but the brain is not doing 64-bit or 32-bit operations either. So the idea is, anyway, that there are interesting things that people want to compute at this level with this precision. I'm not going to claim that this is a brain by any stretch of the imagination, but it's brain-inspired or cortex-inspired, and this is just something we're playing with right now. We're not exactly sure where it's going, but 10 years ago or 13 years ago, I had no idea where this switch thing was going either. So we're moving along with that. Now, having said this, I'm here at Stanford, and so I have to pay homage to the memristor. All right. Now, how many of you have heard of the memristor? Oh, okay, great. The memristor was invented here by 2 people that you should know very well, Bernie Woodrow and this person here, Ted Hoff. Yes. So professor and graduate student, and they were working in the 1950s on neuronal processing. Okay? So they actually built something that they called the Adeline Adaptive Linear Neuron. This is a machine which was essentially set up to compute and essentially be a recognition engine. And the idea behind it was just sort of what I described with these circuits of memristors and neurons. But of course, they didn't have memristors then. They had a memristor. And I guess I have a little bit of time. I mean, that's not a memristor that Ted Hoff is holding there. But the memristor, was an absolutely amazing device that Bernie Woodrow invented. And what it is, it's a 3-terminal memory resistor. And so he essentially came up with an idea for a device, an invention, which was a memory resistor. And he just took a portmanteau of these 2 words and left 1 letter out. And so he invented the memristor, whereas Leon Chua discovered the memristor. So how are these 2 related to each other? Well, it turns out that you can actually draw a very simple circuit element that relates the 2 to each other. The and we've actually built both of them in the same circuit in our lab at HP. So this is the way we did it. We start off with a substrate here, and we make a bottom wire. We then deposit a layer of our switching material, titanium dioxide or some other similar material like that. And then we do an angle evaporation like this of a second set of metals through some sort of a patterning system, through a lithography system. And what we wind up with is a 3-terminal device. Okay? So you see we've got one terminal here, we have a break there, we have a terminal here, and we have a terminal down there. So that's the 3-terminal device. And the way this works is this can be a memristor here. Okay, we can put a bias voltage between here and here, and we can push oxygen vacancies between these two, and we can get these two to switch. We can do the same here. Okay, so we can push oxygen vacancies back and forth between these two guys, and we can get these two to switch as a memristor. Oops, sorry about that. Oh, I'm sorry. No, this is. Yeah.
Stochastic. Stochastic. Forgot about that.
So, but the way a memristor works is you essentially tie these two together, either ground them or whatever. So you tie these two together, you put a bias potential here, and that changes the resistance between these two electrodes. And that's the definition of a memristor. Bernie Woodrow and Ted Hoff made theirs using a number 2 pencil lead from a mechanical pencil that Bernie bought at the Stanford student store in 1959, and a solution of copper sulfate and sulfuric acid. It's a great story. If you don't know it, look it up. It's fantastic. We're doing effectively the same thing here, but at the nanometer scale. So we've got a pencil lead here, nominally something that has a very high resistance, and we're able to push oxygen vacancies into the region between these two electrodes, and that controls the resistance between those two electrodes. And this whole thing, we've actually been able to make a device with a feature size, essentially a gap size here of 2.8 nanometers. Down to that size, and this device actually works. So this is sort of a equivalent circuit using two cross-point devices, two crossbar devices of a memristor with two memristors. But then in this particular case, we essentially collapse that down into one device, one 3-terminal device, and indeed we can see the resistance between these two electrodes changing depending upon the bias that we have applied to that bottom device there. So that was a lot of fun for us, because now we're able to publish a paper that had both the word memristor and memristor in the title of the same paper, and essentially sort of go through some of the history. But really, I need to pay homage to Bernie Woodrow, because he was really the first one, to my knowledge, to really think about the ability to do synaptic type of computing with a memory resistor. A couple other things that we've been doing. There's a lot of angst that's been going on for a very long time about how do you get to 3-dimensional circuitry. Very important thing to do. As you just simply can't scale things down in 2 dimensions anymore. How do you get that 3rd dimension? Well, this is something that's been eluding the community, shall we say, for 30 years, because in silicon we need single crystal in that 3rd dimension. And getting high quality single crystal has just been really, really tough. Well, it turns out that for these memristor devices, it's a thin film technology. This is a material, effectively a semiconductor, if you will, evaporated on top of metal lines, and there's no need for this material to be single crystal. In fact, it works better if in many cases, if it's amorphous. And so what we realized, again, Dmitry Strukov and I worked on this and published a paper in Proceedings of National Academy of Science a couple of years ago, was that we could actually address a very, very large number of crossbars with a single layer of CMOS, if we were somewhat clever about the way in which we do the addressing. Now, if you sort of think about it, most of the schemes that I've seen for addressing a three-dimensional circuit require 3 numbers. A number to specify the x position, the y position, and the z position. And you try to build a circuit based upon that, and very quickly what you find is that Rent's rules choke you to death. That you simply cannot route enough vias through the system to access all of the different devices when you're trying to address every single one with a set of 3 unique numbers. So the interesting idea that we came up with is, well, what if we used 4 numbers instead? And initially that sounds like an absolutely crazy idea. I mean, if you're going to use 4 numbers, that's going to make it even worse, isn't it? Well, no, actually it makes it much better. Because what we're doing is we're putting the system now in a 4-dimensional address space. And if you think about it, it takes a very small amount of CMOS to address that 4-dimensional address space. And so what we did by playing with some solid geometry and this concept of having 4 numbers required to address every bit in the system, we figured out that we could actually build a 3-dimensional structure in which a single layer of CMOS could, at least in theory, address 1,000 or more layers of memristors in crossbars on top of it. I'm not going to go into much more detail than that. I don't know how to explain this in less than 6 hours. I've never successfully done it. We've had many discussions where people have come and we've sat down with them. We've given them the paper. We've described it. And usually it's several hours after our discussions over drinks that all of a sudden you see the light turn on and people saying, ah, yes, now I get it. So I wish that I knew how to turn that light bulb on instantaneously for people. But all I can tell you is that it's a cool trick, and it's just one that I don't know how to explain other than to say it really does work, and you just kind of have to think about it. But if you can do it, this is the type of thing that you can actually start to think about making. What if we actually build systems that look like this, where we actually just completely collapse the computing hierarchy down to a single chip? Okay? So we have a layer of CMOS down here, which is our control layer. Then we have a layer of memristors here in a crossbar, which is our logic layer, because I've just shown that we can perform universal logic with memristors. Then we have a layer here which is, maybe sort of like a cache, and then a memory, and then a storage, or somehow all mixed and mashed up. And in fact, it doesn't even have to be hierarchical like this. The logic and all of these different types of memory and storage can all be mashed up inside of each other. And in fact, they can be dynamically configured at any given point in time. You can decide at any point in time that any pair of memristors in this thing can be an implication logic gate. And so here the idea is that you're actually distributing the computing in your storage. So you're taking the computing to the data instead of trying to haul the data to the computing, do something with it, and then shove it back. So this is, again, it's an idea that we're playing with. We've got a long way to go before we actually implement something like this. But it's a lot of fun to think about. And I think I have run out of time, so I should just go ahead and skip to the end. And thank you very much, and see if there's a couple of quick questions. Yes?
Yeah, question. In terms of, let's say, a 2-dimensional memory array access device, are you thinking of just another memristor? So you have 2 in series, back to back, or how? Otherwise, you just have a bunch of resistors that have sneak paths all over the place.
Well, in fact, what we're doing is our access devices are it's CMOS, and for a memory, this is our picture of a memory here. And so we are thinking that our memory is going to be a multi-layer system. So the issue is that you've got CMOS here, you've got some really sparse set of vias that you need. You don't need that many vias, as it turns out. And if you do it cleverly, what you find out is that in a structure like this and in an idea like this, physical neighbors are not logical neighbors. So if that worries you, if it makes you feel queasy, that could be a problem, because what can happen is that 2 adjacent bits in something like this can be very, very far apart in terms of logic space. But that may actually be a good thing. You may like that.
You're still going to have a lot of leakage current. You're just going to try to minimize its.
Well, all the leakage current is going to be in the CMOS down here.
Oh, I meant the sneak paths.
Sneak paths. Oh, that's a great question. And I didn't have a chance to really talk about that. I mean, and that's another whole lecture that we could get into. We have been worrying about sneak paths for 13 years. And so it turns out that for a bipolar switch, the idea of using diodes doesn't work. So you have to do something else. So what is the something else? Well, it's nonlinearity. The fact is that these IV characteristics that we get with these devices are highly nonlinear. I showed you this exponential of an exponential type thing. So these things are so nonlinear that we can actually use the nonlinearity in the IV curves themselves as the isolation device.
Once you program with those, it'll be in the other states, so you will no longer have the same, be in the same part of the diode curve, let's say.
Well, I mean, this is all true, and so you have to. The size of the array that you can address with a particular block of CMOS depends upon the amount of nonlinearity in the IV curve. And so we're not talking about addressing gigantic blocks. Okay? We're not talking about doing, say, 10,000 by 10,000 arrays. We're talking about doing smaller blocks, but having them go up in the third dimension. And sort of never having more than 1,000 devices acting as potential sneak paths in the crossbar. Correct. And so you're absolutely right. The limiting factor in all of this is the amount of current that your driving circuitry can put out when you're trying to read the device. Okay, and if you try to make a very large system and you've got all these sneak paths, you need a gigantic transistor in order to put out that amount of current, and that actually winds up being the limiting issue in terms of the total block size. So if you want to get all of your CMOS circuitry underneath the arrays that you use here, everything has to be very finely tuned in terms of the properties of the drivers, the current that you can, and the nonlinearity in these devices.
So why doesn't the diode work?
Because these devices are bipolar. You have to both switch them on and off.
So you need a bidirectional diode. Basically.
Exactly. So you need something that.
You should invent that next.
Okay. All right. So here, there it is, right there.
Memristors back to back, right?
So here's the bidirectional diode.
Yeah.
This is a current-controlled negative differential resistor.
So you've got one. So why not use it?
Who said I wasn't?
Okay.
Okay. So you're just so smart that you anticipated all of this without me showing it to you. So in fact, you can build. It turns out that TI-407 undergoes a phase transition. So it's already there. Now, unfortunately, the phase transition occurs at liquid nitrogen temperatures. But there's other materials that have phase transitions that are above room temperature. But for this particular example, we essentially looked at TI-407, and at low temperatures, it's an insulator. At higher temperatures, it's a metal. And so you run current through it. The current heats the device up, and that actually causes the device to go through the phase transition. So it goes from insulator to metal. And so you actually get a negative differential resistance in the device, and it's bidirectional. So at low currents, if you essentially set this thing up here like this, such that your half voltage is somewhere right here, this will block anything, any current from going in either direction, either forward or backward in your devices. Whereas if you exceed this, you essentially can sneak around the corner here, you can get up here, and you can actually perform your reads in your system. This is a phase change material. And as I said, just by accident, we discovered that TI-407 has this property. It's not the only material. VO2 is another material that has this property. And so it turns out that these devices, even though they're phase change materials, because they're small, because the volume is at the nanometer scale, you can actually switch them, again, in less than a nanosecond. So here is a device which was essentially, this one was, I think it was, this is actually kind of a big one. This is 50 nanometers in radius, 100 nanometers in diameter. And we were able to switch this in less than 400 picoseconds. So this is going from its off state here to its on state in less than 400 picoseconds. And again, this was actually limited by the capacitance of the oscilloscope for this particular measurement. So if you make it small enough, you can still get a very significant resistance change, which looks like diode control, but it's bidirectional. And because it's thermal in the way it goes, you sort of worry about that. But because it's small, because the volume is small, you can actually get it to switch, again, in less than a nanosecond. And so it's time matched with the time characteristic of the device itself. And again, it's bidirectional, like that. So this works very well. We're not using titanium Ti407, obviously, but as I said, there's other materials that are known that have this particular property. And you put one of these in series with a memristor, and it gives you this nice non-linearity, this nice blocking characteristic in the for blocking sneak paths. Next question.
You talked about potentially a flash replacement. How about DRAM replacement and SRAM replacement?
Let's put it this way. The low-hanging fruit right now is it's flash and hard disk. Okay? That's our first target. Very shortly after that, we're going to make a shot at DRAM. How long? I don't know. I sort of showed you the. This plot here. We're within what we think is 1 year of demonstrating the type of endurance that's needed for a consumer type of DRAM in a consumer type of device. For a enterprise type of device, we need to be a couple orders of magnitude better than this in terms of endurance. However, right now, we actually don't know what the endurance of our devices are. They haven't died yet. We're still testing them. So we'll see. We'll see where we wind up. Now, all of that said, we get the endurance, and there's still a couple of issues. We're still not quite competitive with DRAM in terms of switching energy yet. We're actually pretty good in terms of speed. We can switch them about as fast as DRAM. But right now, our existing devices require more energy to switch off than for DRAM. On the other hand, these are non-volatile devices. We don't have to burn all sorts of energy to keep their state. So there's interesting trade-offs here, but it'll be a few years after we have something in the market for flash that will be able to address DRAM. What those time frames exactly are, I'll be quiet on, but it's not 10 years.
And so how about on-chip cache like SRAM?
Well, that's right after DRAM. I mean, we've got these. Let's just say that we've got these things lined up, at least, in our minds, and what I will tell you is that we are actively working on all of these things. These are all things that we want to achieve, and of course, having a multi-core processor in which all of the memory and storage that you would ever need is on the chip itself would be kind of cool. And that's a goal, and it's one that we think, I hope that I see before I retire. Let's put it that way. Yes, question of you.
I'm a software guy, so most of this talk went over my head. But as you were describing what the computational architecture at the end, I was thinking of something that's been floating in the computing literature for a long time, which is data flow machines.
Yes.
Have you thought about?
Well, I mean, that's completely over my head. I mean, I talk to my colleagues at HP Labs, and they get all excited, and they start talking words that I can have no idea what they mean. So you know, I think that one issue that I do understand is this whole issue of essentially collapsing down this hierarchy, where everything is byte addressable, where absolutely every piece of information that you want has an address, and you can fetch it directly with that address. And so how, you know, that I think plays into some very interesting issues with respect to software, and then how one utilizes that, I think, depends upon the specific application. Yes, question?
Yeah, in one of your earlier slides, you had that SPICE and a circuit design group, and then you had an ECC group.
Yes.
Where's the source of noise in this?
Well, so I mean, again, this is like the very first experiment that we ever did on these, and it was completely open loop, and so there was no feedback or anything else. But you can see that there's noise. These devices, there is the stochastic issue to these devices. You've got these discrete particles, and so you hit it with a pulse, and it's not going to go to the same resistance every time. In fact, it's almost guaranteed not to go to the same resistance on consecutive pulses. And so at some point, you're going to make a cut through here, and you're going to decide somewhere is on, somewhere is off, and what happens if something doesn't achieve that transition. And so what we're doing is we're actually getting a lot of statistics so we know what the bit error rate of these devices is, so that our error correcting guys can essentially choose the right code to use and tell us how much redundancy that we'll need in an array in order to be able to compensate for that level of problem. But this issue of sort of the switching noise, and this other issue that I talked about, the fact that the devices have a log normal switching time. You know, one way of dealing with that is one way of dealing with the log normal switching time is just to put a very, very long pulse on the devices. But boy, that wastes a lot of time and a lot of energy. And so another way of doing it is just to say, hey, we're going to select a fairly narrow pulse, and we know that statistically, some fraction of the time, the device isn't going to switch. And so given that, what's the appropriate error correction scheme to how much redundancy do we need to put into the system in order to achieve a bit error rate of, say, 10 to minus 21 or whatever. So those are key issues, and it's the error correction guys who in the end save our bacon, because you actually calculate out what you would need to do in terms of time and power and whatever else, given these sort of skewed distributions that we're getting, these log normal types of distributions, and these things don't become all that competitive then because of the very long tails. But if you can chop the tails off, and you're using these sort of fast, the average fast time, then all of the nasty stuff gets taken care of by the ECC. Everything that I've done here that I've shown is room temperature. We're just now starting to do some higher temperature type stuff. We've also done experiments where we've taken devices, we've heated them up to 400 C, cooled them back down, and then operated them. So at least in that type of environment, they're okay. We're just now essentially have an oven that's set up where we can actually do accelerated testing, accelerated aging, and operation at accelerated temperatures. Of course, you know, when people are very, very interested in how these things will operate at 85 C. So we've collected data at room temperature. Now we've got to do the same thing at 85 C and higher. Next question.
Traditional DRAMs have troubles with cosmic rays and alpha particles and things like that. What do those do to your toys?
The memristors themselves are completely immune to ionizing radiation. And we know that because we've actually taken some of them over to Berkeley, to the 88-inch cyclotron over there, and we irradiated them with enough 1 GeV bismuth ions to simulate 500 years in orbit in the Van Allen radiation belt. And we measured the devices before and after this exposure, and we had devices in both on-state and off-state and various other states, and we actually could not measure any difference in the devices before and after that level of exposure. We've done something similar with gamma rays, and after having done that, all of a sudden we had people breathing down our necks about export control and other things. And so now what we say is, we don't do that anymore. We don't care. We don't know. We don't want to do, and so people ask us for samples, and we sort of, give them a sample, and they go off and do their measurements, and we just tell them, please don't tell us what the answer is. But at least the one experiment, the one paper that we did publish in the area says that they're completely immune to ionizing radiation, and you can understand why. They're amorphous. The materials are amorphous materials. How do you screw that up?
So another software-oriented question. You mentioned that this enables a sort of analog form of computation.
Yes.
So can you comment on whether there's a possibility that this could enable a stronger model of computation than the Turing machine model?
Well, I would have to say that that's totally beyond me. That's not my area. I'm not sure that this is a stronger model of computation. In fact, it's probably weaker in some sense. It's just different. It's just a way of doing computation where you don't need a precise answer. I mean, that's really what this is about. So much of computation that's done today does not require a precise answer. It doesn't require an answer. I mean, look at the machines that we're using to do a Google search. And look at how much garbage you get back from a Google search, right? I mean, and yet there's a machine out there that's calculating numbers very, very precisely to give you a bunch of garbage back. Well, I mean, what I'm saying is that there's got to be better ways of doing computation which is geared toward search and decision making, where you don't worry about 32-bit or 64-bit precision, but you want a better answer that you get out. And I think that that's what this gives you. But in terms of being able to state with precision that you can calculate a particular thing, I think this is probably worse than what you'd get from a Turing machine. But that's okay, because it's a different type of thing that we're looking for. We're not asking the same question.
Would you expect it to be possible to emulate this effect in organic molecules if they were designed correctly? Or?
Well, yeah, I think actually we were seeing some of it in these organic molecules that we were playing with. The problem that we ran into is that we burned them up very quickly. Instead of having endurances of 10 billion, we had 10. And so other people, and we and other people have looked at polymer systems. We've looked at organic systems, and we just sort of haven't figured out how to put these types of fields and currents through an organic system without cooking it. And that was really, at the end of the day, why I went over to inorganic materials. I mean, I finally got tired of frying eggs and said, there's got to be something else. And so that's when I started looking at these inorganics, and they are a lot more robust. Yes, question.
The mechanism of leakage.
The mechanism of what?
Leakage.
The mechanism of leakage. There is no leakage. I mean, in terms of the idea of leakage in a transistor type of system. I mean, these are tunneling devices, but the issue is that you only power these devices when you're switching or reading them. And so in some sense, everything is real signal on these devices. So you don't have any power on the system to hold state.
The oxygen try to diffuse.
Okay, well that's a different question. So that's asking what is the state lifetime? So what I said was that we've got drift and diffusion operating in opposition to each other. And so if I take a device and I switch it from one state to another, in, say, 100 picoseconds. And then I just ask myself, well, how long would it take by diffusion alone for it to switch back to its initial state? Okay? This is where physics comes to the rescue. If you take the Nernst-Einstein relationship, which is taught in most textbooks, about the relationship between drift and diffusion, and you plug in reasonable numbers, what you conclude is that the maximum difference, the maximum ratio of switching time to state lifetime should be a factor of 1,000. So in fact, early on, when we were doing experiments, we were switching devices, and we were seeing switching times of like a microsecond, and we were seeing lifetimes actually of years. And so that caused us to scratch our heads, because, I mean, after all, Einstein, you know, how could he be wrong? Well, in fact, it's the Nernst-Einstein relationship. That's how we got out of it. There's not a law. And in fact, it's the Nernst-Einstein relationship is explicitly for low fields. At high fields, things go wildly nonlinear. And so what happens is that at high fields, the drift of these oxygen vacancies is not proportional to the field. It's exponential in the field. And so you can get 20 orders of magnitude in dynamic range in these devices, because in fact we're at very, very high fields. You know, a couple of nanometers, a volt or so, that's an extremely high field. It's not quite the breakdown voltage, the dielectric breakdown voltage, but it's high enough that you get a very exponential acceleration in the drift velocity. So you can have drift of 10 meters per second. And then you ask, how long does it take to diffuse back? Well, given some of the numbers that I found in the geology literature, which is where you find the better numbers, you calculate numbers like 100 million years. So now, there's all sorts of other stuff going on in these devices. There's, you know, because there's fields and whatever else that are going on. But we've built devices now. We've got devices that we've had in our hands for over 4.5 years. And we've set their state 4.5 years ago. And we come back periodically and we measure them. And we have not been able to detect any change at all in their resistance over a period of 4.5 years. This is on the shelf, at room temperature, all of this other stuff. But, you know, from the theory that we have, from the measurements that we have, these things really look non-volatile. And, you know, at first it's surprising. If you know about the Nernst-Einstein relation, you're skeptical, and you should be. We were. And really it was Dmitry Strukov who sat down and derived this exponential relationship for the drift velocity of the vacancies. And we got all excited about that, and we started writing up a paper for Nature. And then, of course, I made the big mistake of saying, well, gee, can we find anything like this in the literature? And sure enough, we did. 1940, Neville Mott derived the same formula back then. So this is actually something that's been known for a very long time. But it's a nice piece of fundamental physics that actually saves our bacon in this case, because it gives us this huge dynamic range between how fast you can switch it and how long the state lives.
Given the time frames you're thinking about, are memristors relevant to exascale computing designs, and are you actively considering them for those kinds of applications?
For us, memristors enable exascale computing. We don't think it's possible without them. For a lot of reasons. I mean, one is just the 3 millisecond latency that's required to get data from a memory into a hard disk. You know, there's and the energy required to spin all of those hard disks. I mean, a hard disk is, even if you're not using it at all, a hard disk is using 8 watts of power. That's just to spin the disk. So it's using 8 watts, and then you're using another 4 watts just to cool the thing at the back end. So that's 12 watts, and you're not even doing anything with it. Whereas the memristors are completely proportional to their use, right? So they're very low energy anyway, and you only are energizing them when you're reading and writing them in the act. So the amount of power required is very much lower, and the fact that now you've got something that's byte addressable, so you can, it's random access, so you don't have this long thin hose that you're trying to suck it through. So you go from latencies of milliseconds down to hopefully microseconds or even less. So frankly, there's a small group of us anyway that don't think that exascale is even possible without memristors. That in terms of time and power requirements, if you can't get rid of all of that other stuff out there that's hanging off the end of it, the core part of it can't keep up.
Stan, I thought the issue was the DRAM power, not so much the disk power.
Well, what we would like to do is we'd like to replace it all.
Yeah, well,
We'd like to.
DRAM's a bigger issue, I think.
We'd like to. Eventually, we'd like to be able to essentially collapse that entire hierarchy and replace everything from disk to through L3 cache with memristors.
Yeah, well, you still have the capacitance of the access lines, the DRAM, and your
Absolutely.
the power on hog.
Absolutely. So
3D stacking helps.
So there's all sorts of tricks, but I think that just a large part of the delay. I mean, the reason why things have taken this hard right turn, as I said, it's not the bottleneck is not the computation anymore. The bottleneck is in the communication, and it's everything else. And so you've got to open up the pipes somehow, or get the data much closer to the computation, or actually get the computation inside the data, such that your communication paths are microns instead of inches or even longer. So that's really the issue. And I think you're probably familiar with the paper that Partha Ranganathan wrote earlier this year, in the January issue of IEEE Computer. He essentially presented the architecture that we're thinking about. He calls it nanostores, which is this sort of distributed cores in storage concept. So that's really how we think that exascale can be done. It's a mixture of that plus some photonic interconnect, which of course is a completely different story, but also in my lab. Fun things that we're doing. Yeah, question.
So what you're talking about is collapsing, reducing the von Neumann bottleneck.
Yes.
Traditionally called that.
Mm-hmm.
And you talked about rethinking logic in terms of the material implication and so on.
That's certainly further down. I mean, we don't think that exascale requires that. Okay.
Well, I mean, the thing with exascale isn't DRAM and collapsing the von Neumann bottleneck. That's obviously a necessary requirement. The issue is having to move the data at all.
Mm-hmm. Yes.
So, I think that was essentially my point. Is that you're collapsing the von Neumann bottleneck is one thing, moving the data at all is another. So the obvious question is, why not rethink the very nature of memory? You're still thinking about memory in terms of storing bits and bytes.
Yes.
Understood it, right?
Yes.
So I would suggest that maybe rethinking.
Well, I mean, that's where this whole synaptic thing is coming in. I mean,
well, you're still using the connectionist model from what I heard.
Well, yeah.
That still ends up with switches and potential weights and so on.
Well, it sounds like a really fun research project. I got to figure out how I can get my boss to fund me to play around with that one.
I think you'll talk, by the way.
Oh, thank you.
Question. Noise data. Did you check if the relation between noise and resistance still holds in the traditional passive device?
No. I mean, the issue is that this noise that you're seeing is not thermal noise at all. This is, it's orders of magnitude larger than the thermal noise. And so this, again, it's the stochastic noise of the fact that you've got a finite number of oxygen vacancies, and they're moving around via essentially random processes in the system, and you do a switch on the device, or even if you're just sitting there holding it, trying to measure it at a particular state, things are still moving. There's still some fluctuations, and so those fluctuations that you see are not the types of normal thermal noise you predict. It's very much larger, and it's because of things jumping around in a field.
I'm not shutting you off. I'm just taking away the show off.
Okay.
Now all the cool stuff is going to happen.
For more, please visit us at stanford.edu.